Okay, so we saw that in the previous example we found that the acceleration in the moving reference frame relative to the charge distribution is not equal to the acceleration of the charge in the reference frame, which is fixed with respect to the charge distribution, and they differ by this factor epsilon naught mu naught times velocity squared, velocity of the observer squared. So again, the two observers do not agree on the expected acceleration, and this raises some really important and deep questions. Particularly, can they both be right or wrong? Who's right? Can they both be right? Or are Maxwell's equations wrong? What's going on? Okay. And it's interesting to note that the difference here between these two accelerations, observed accelerations, is at least proportional to this factor epsilon mu naught. So let's ask the question: what is the meaning of it? What is the meaning of that factor? Of this product of both of these things are fundamental constants. So again, this is the permittivity of free space, and this is the permeability, the magnetic permeability so these are two fundamental constants, and we have this, they crop into this little relationship here. So what's going on? Okay, so we have to, first of all, we have to remember our Maxwell's equations, which hopefully you're familiar with from electricity and magnetism course. So we have this equation which relates the divergence of the electric field to the charge density. Okay. We have an analogous equation. Let me draw a line here just so that I keep things straight. An analogous equation for the magnetic field: the divergence of the magnetic field equals 0 in the absence of a current distribution. We have the curl of the electric field is equal to the negative time rate of change of the magnetic field. Okay, and the curl of the magnetic field is equal to this permeability times the whatever charge distribution, current distribution there might be, times again this product that we have, times the time rate of change of the electric field. Okay, so we see that these constants are cropping up here in our equations. Okay, so if we think about propagation of electromagnetic waves, light waves, in a vacuum, okay, and so we can set this in vacuum, so we can set the charge distribution and the current distribution to 0. Okay, so that goes to 0, and that goes to 0. Alright, so now we do just a little trick. You may have seen this. We basically take the curl of this equation right here. Whoa, hello. The curl of this equation right here. Okay, and that, just if you plug it in to Maxwell's equations, gives you the curl of the right hand side of that equation. Okay, and we can simplify this. This is equal to minus the time rate of change